The first 24 hours after a nuclear detonation are unlike any other emergency humans have ever studied, because the greatest threat for millions of potential survivors is not always the brilliant flash, the collapsing buildings, or even the deafening blast itself. Those terrible events unfold within seconds, but for anyone outside the immediate zone of catastrophic destruction, survival begins only after the explosion has already happened. The choices made during the next few minutes and the following hours can dramatically influence radiation exposure, injury risk, and long-term survival. This is the period when instinct often becomes the greatest enemy. Every natural impulse urges people to run outside, search for loved ones, drive away from danger, or gather information with their own eyes. Yet decades of research into nuclear weapons effects, civil defense planning, radiation monitoring, atmospheric physics, emergency medicine, and accident response repeatedly demonstrate that many of these instinctive reactions can increase danger instead of reducing it. Understanding what actually happens during the first day requires separating dramatic images from physical reality. A nuclear explosion releases energy in several forms simultaneously. Intense thermal radiation creates extraordinary heat capable of igniting combustible materials over large distances. A rapidly expanding pressure wave follows, producing destructive overpressure that can shatter structures, hurl debris at tremendous velocity, and transform ordinary glass into thousands of razor-sharp projectiles. Prompt radiation emerges during the earliest moments, but for people beyond the most heavily damaged zones, the longer-lasting concern becomes radioactive fallout, an invisible hazard that depends on wind direction, weather conditions, particle size, terrain, and the altitude of the detonation itself. Many people assume radiation spreads evenly, like an expanding bubble across an entire country. In reality, fallout behaves more like contaminated dust carried by atmospheric currents, concentrating heavily in some locations while leaving others with comparatively little contamination. This distinction becomes critical because survival depends less on distance alone than on understanding where fallout travels, how rapidly it settles, and whether someone remains protected while those radioactive particles continue descending from the sky. One of the most persistent misunderstandings is the belief that speed always equals safety. Immediately after witnessing a distant mushroom cloud or experiencing a massive explosion, countless individuals would likely attempt to evacuate by vehicle. Modern cities already struggle with congestion during ordinary rush hours. History shows that even relatively small evacuations caused by hurricanes, wildfires, industrial accidents, or severe weather frequently overwhelm transportation networks within minutes. A nuclear emergency would multiply those problems enormously. Roads become blocked by damaged infrastructure, disabled vehicles, emergency responders, frightened populations, fallen power lines, traffic collisions, and disrupted communications. Every additional minute spent outdoors or trapped inside a vehicle while radioactive particles begin settling increases unnecessary exposure if the evacuation route passes through contaminated areas. Emergency planners have therefore emphasized a concept that initially feels counterintuitive. In many circumstances, immediate shelter is significantly safer than immediate evacuation. This recommendation is not based on fear, but on physics. Gamma radiation emitted by fallout particles weakens dramatically when dense materials absorb its energy. Concrete, brick, packed earth, steel, and substantial building mass reduce exposure far more effectively than automobile doors, vehicle windows, or lightweight residential walls. The objective during the earliest phase is not permanent isolation but temporary protection while radiation levels decline naturally. Radioactive isotopes begin decaying from the moment they are created. Although some remain hazardous for years, the mixture responsible for the greatest immediate danger loses strength rapidly during the first hours and days. That decline does not make the environment harmless, but it means every hour spent inside an effective shelter during peak fallout can prevent a substantial amount of cumulative radiation dose. The timeline begins with the flash itself. Light from a nuclear detonation travels essentially at the speed of light, arriving before sound or the blast wave. Individuals located many kilometers away might first notice an extraordinarily bright flash, often brighter than direct sunlight, even through clouds. Looking directly toward the source can injure vision, while exposed skin may suffer thermal burns depending on distance, atmospheric clarity, and line of sight. The blast wave follows seconds later, or EV.